Hello, good morning. Your question about the asymptotes is actually a very good question because it's sort of worth understanding why that graph that you sent was not an asymptote. And it kind of gets into the more interesting parts of mathematics. See, most people think that mathematics is logical and rational, and it is, but there's a lot more creativity and imagination that goes into it. I started recording and okay, so let's take a look at this three balls that are in a box, and let's say there's a table nearby that has four balls. Okay, now you put the box on the table. Now suddenly all the balls have fallen into the table, and now you have 7 balls. We can model this by saying 3 plus 4 equals 7. Notice how the nature of this is countable. You can count these balls either on your finger or in your mind, but in a finite manner. They're real and they're finite. This is most mathematics. Arithmetic is just adding, multiplying, all these things that we learn in school. These are discrete mathematics, real world scenarios. Now, discrete mathematics is all cool, but there's something way cooler about mathematics, and that's alluding to the earlier said abstractness. That's continuous mathematics. So in continuous mathematics, you have a function that is equal to something, say x squared, right? And what happens is that in discrete mathematics, you have the constraint of real world. So if you have 3 balls and 4 balls, you can only have 7 inputs, right? There's only 7 things to take and modify. In continuous mathematics, that number is no longer a number, but an idea, and the idea of infinity. Most people think of infinity as this huge number, and it really is, but infinity is not even a number. It's just the idea of a number that never stops, right? So where does this come with your graph? Well, let's take a look at your graph, right? Your graph was this bunch of points about experimental data. They were connected using a line, and it had this sloping thing, right? And you said that it's an asymptote. That is entirely incorrect. See, for something to be an asymptote, right, so let's just say 1 over x, it has to have that curve and has to be approaching a specific value, say 1. But there's something else that is interesting. An asymptote never actually reaches its value. It only approaches it. So the only time you would ever reach this value is at the idea of infinity. So 1 is only reached at infinity. Your graph was a real world experiment, right? With real world data points. So when the lines connected those data points, they represented a finite, discrete structure. It was never reaching infinity because there was no infinity in real world, right? And since there's no real infinity, it's not approaching a value at infinity. What you really should say, this is not me, I'm not trying to correct you, I'm just trying to help you understand mathematics better. That sounded like what you really should say. But what the real right word, a better word, would be that it was logarithmic. It was a log function. Now you would say, wait a minute, but isn't a log function also a function and thus infinity? Yeah, no. Functions can have constraints, right? So a function can be just 10 units big of 10 inputs. An asymptote has to be infinitely big, right? It has to reach infinity to reach that value, or approach infinity. That's the correct term. So logarithmic would be the right term in this case, because logarithmic functions kind of look like this, where there's a decay. So a cool fact, just because I have a little more time to kill for you, this is an exponential function, right? exp. Usually what people say when they're like talking about hyper increase is exponential function. But if you were to draw a line at the over here, and make a reflection of this exponential function. This is poor drawing, but you get the logarithmic function. Fun fact, yeah, because they are inverses of each other. So next time you see someone say anything about real world data and say asymptote, you can tell them this cool story about how asymptotes are actually only in infinity. This is really important, by the way. Asymptotes and infinity created the idea of continuous mathematics. Continuous mathematics meaning the entirety of calculus. I'm taking 5 semesters of calculus, so think about that. It's a huge field of mathematics, and it allows us to do really cool things in the real world, because turns out when you can model infinity, you can then put it in real world and just have really cool insights about real world data. I am sorry for making such a long video. I truly am, but if you learned something, yay. If this is a lot of confusion, I'm really sorry. I tried.